So I'm going to present my PhD thesis, and I've submitted it in September 15, and I'm going to discuss it in a couple of months. So it's a real first time for me, not only at Getty, but also for this specific subject. And so I'm very pleased to do it here. And I really hope that this will, the subject I'm going to describe are going to open up for discussion, because one of the things for me that's been difficult is that part of the research I've done did not find much correlation with existing literature. So basically, I felt a bit alone. And so one thing, the first part is going to be about the construction of a machine, which is not, well, maybe a bit too close to Max, which is not very new, because there have been several biaxial testers in conservation science history. The other part is going to be the quantification of historical textile morphology. Oh, sorry. And you see, the point is that when I was about to test the mechanical properties of the historical textiles, I realized that there was very little literature about the measures, the quantitative description of the yards inside the textile. So I'll give you a very short presentation of this, and luckily I have a poster about this. So there is much more information in there, and hopefully we'll have time to discuss. So the next important points are these: the tensile modulus and of textiles and naturally aged paintings, and the flexural modulus of paintings. And well, let's go ahead. So this is the machine I built during my PhD, for the first year of my PhD. It was a collaboration with my precious friend, Dr. Miguel Sanchez at Universidad Politécnica de Valencia. And we worked during the COVID. So I was in Rome, he was in Valencia, and he wrote the software, and I made the machine. And this is the small clamps. You see, these are the clamps for the sample, and the sample is 10 millimeter wide, with plus a clamping area here. And for clamping it safely without damaging it, I built a 3D printed support, and then it can be clamped without damaging the paint layers. Okay, now the 4 actuators can move independently with an asymmetric motion or with a symmetric motion. Now, asymmetric motion is useful for uniaxial testing, basically, while symmetric motion is necessary for biaxial. And this is, you see, a commercial biaxial tester, which is having a symmetric motion. I mean, I showed this because you cannot do fast testing on an old sample. So this was available. It was nice. And but basically, the point is that when you are doing a biaxial tester, you want to have the center of the samples in the same location, because otherwise you get distortions. So this is the CAD drawing of one of the 4 identical 4 actuators. And this is I started from the welding of the cross, the steel cross, and then I had these parts laser cut and assembled it, and some parts were commercial, some others were handmade. And so this is the final execution of the one of the identical actuators. And you see that they have a load cell here, and each load cell reads the force on the sample. So in order to start with the symmetric disposition of the forces, we did a pretensioning algorithm that allows, changing the force and the position of the sum of the clamps at all time for this relatively short time. In 90 seconds, you get, 100 seconds, you get to the pretension mean value of 0.3 Newton centimeter, which is a quite low force, which is good for starting always in the same conditions. And so now, why was a new biaxial tester needed? Well, the point is that I need to go into, I'm a PhD student, but I'm also a conservator. I've been 35 years in conservation, and I started doing research on elastic tension of paintings in '92. So when I was a student, and I never stopped basically. So what happens is that my PhD research was based on two major conservation projects. One is the design and construction of a new strainer for the oversized Frank Stella painting, and it's a Getting Conserving Canvas project in Santiago de Chile. And the other one is the design and construction of a new strainer for Rembrandt's Night Watch, and also the choice of the elastic tension, the value of the force of the elastic tension. And of course, these are not very easy tasks, but I mean, I had enough experience for approaching them. But the point is that I will show you what happened in the meantime. But this left me with two major questions about the tensile modulus and the flexural moduli, because they are very it's not so easy to calculate them and use them for digital models, as we have seen already this morning. So this is the Frank Stella painting, and we did the tensioning system with the springs that allow measuring the force. You see here there is the length of the spring for that location, and once you have the force selected, you can do simulations and you can do predictions of the behavior of the painting. So what we did a simulation of the forces needed that were optimal for the painting before I went to Santiago. And then when I arrived to Santiago, I was confronted with this prevision of the elongation of the painting, which was wrong. I mean, it didn't match with reality. I didn't see that much deformation in the painting. So what happened is that I had done uniaxial tests on samples of the same canvas with Alain Roche, who unfortunately didn't manage to come this symposium, and we did it in warp, in weft, in 45 degrees, and all these numbers were put into the FEM model. But what happened is that the deformation were much larger than the real. So when I was there, I tried to figure out with the engineer in Torino what happened, and then I realized that as everything was okay with the model, I realized that the problem was with the uniaxial testing. So I did a biaxial tester with pieces of wood and springs and a caliper, and so I did it in one day. And the numbers I got with a much larger sample, of course, it was 100 by 35 centimeters, even though it was rougher estimation, of course, but the numbers were good enough for making the model fit. So I realized that a biaxial tensile tester was needed. So this is a piece of basket weave lining canvas, which was actually used for the Night Watch, but we're not going to discuss this in this moment. But you see that it has a very different shape in the yarns. These are the warp yarns; they are very crimped, and the weft yarns are very straight. So if we do a uniaxial test, we see that there is, of course, the warp yarns are much more giving because they have a very important decrimping phase, whilst the weft yarns are much less, they're much more prone to react. So if we do a biaxial test on the same canvas, we see that there is stiffness transfer. So the warp yarns are a little bit stiffer, and the weft yarns lose some of their force. So if we look into the crimp values, we see that the weft yarns have only 1.6, while the warp have 7. So this big difference makes the difference. And what is interesting, what was very interesting for me was not only to discover this, because it's been anticipated in many research before, was that I measured the value of crimp in the canvas. So looking into 26 samples of naturally aged, well, old canvases from paintings, most of them are from paintings. You see, this is the full list, and we have the dates, and this was the lining canvas we saw just a second ago, and these are. So here we have general data like date, grams per square meter, pH, thickness of the canvas, and then we have the yarn width, which is not very commonly measured. I managed to do sort of a small statistical evaluation with at least a weighted mean. So in the same. I'll show you later. And then the yarn thickness also. So because the yarns have an elliptical shape, so we have the major axis, that is the yarn width, and the yarn thickness is the minor axis of the ellipsis. And then we have twist per meter, which is also very hard to find in literature. But I found a paper, 1973 paper, that allowed me to do the measure. And then the crimp, which is also a relatively complex thing to measure with old samples. Because, for instance, Christina Young and others had used the Pierce model, which worked very nicely for modern canvases. But I tried it on 16, and then it was not working, and I tried it again. I started again. It was really painstaking, and at the end I realized that it simply did not apply to very complex waveforms. So I had to find another way. So, and then the thread count. So this is the samples are all laser cut, because laser cutting is gentle, doesn't do any mechanical damage to the samples. And I draw indentations in the weft direction so that I don't get confused when I test them. And I keep track of the direction. And we have identical testing areas. So the weft yarns have higher modulus in 92% of the cases. And that is 24 out of 26. So modern and naturally aged old samples. If we look at the behavior of the decrimping zone, we see that the crimp is definitely playing a role. And if we look at the crimp in the weft yarns, we see that the weft yarns have a lower crimp also in 26 samples out of 24 out of 26. And so we have a direct correlation. And I found many direct correlations like this, which I don't have time to show you here. But so I wanted to go to the problematic part of the paper, of the talk. So here I would very much like to have feedback. We have 3 days, and I'm very happy with this to be on the first day. And the point is that when you measure the E modulus, you have force over the section and over strain. So basically, when you are changing the cross-sectional area with the same results on the rest of the formula, you change a lot the force. So the E modulus, sorry. So the other point is that when you talk about E modulus. I'm not an engineer, but I learned this at my expenses. E modulus is made for comparing materials and for predictive simulations. So, but this is made for steel or similar things and not for canvases, because canvases have a lot of voids inside. So not only between the yarns, but also within the yarns. So that's, there were several calculation methods over time to extract the cross-sectional area of the fibers. And we had interesting discussions with Emanuela a few months ago, and this is Mario Mecklenburg's approach. I mean, Art in Transit, 1991. And after that, basically, the estimation is around 20–30% of the textile cross-section. So, as I had all these numbers about the textiles I studied, I devised this very simple equation, which is based on the tables I showed you before. So basically, the numbers in black, the values in black are all constants, and the red ones are extracted from variables extracted from the tables. So we have the width of the yarn, the thickness of the yarn, thread count, and the crib. So using this, you can see the difference between the E modulus of the 26 textiles measured with using the thickness of the textile measured with the micrometer, or using the fiber cross-section calculated with the equation I'm proposing here. So basically, you see that there is a major increase in the elastic modulus, and this is the ratio. So we see that this is not neutral. So what happens is that testing samples of paintings, as I have about 100 for the moment of old paintings with a date and all the historical data available, and I'm just starting now. So basically, but I started from the simple side, so just the canvas. Now, but when you have to add the and here we have two unlight paintings with paint layers on, and this one also have wax resin impregnation. So the elastic modulus changes, and the paint layers and treatment influence the modulus and thickness. So what about a lined painting? What shall we take? The two canvases, one canvas, only the lining canvas, the paint layers, the adhesive. I mean, it's a relatively controversial thing, because here we have the numbers for the material actual thickness, but how shall we calculate it? And this is definitely an open question for me at the moment, and I would very much like to discuss it. The other point is that I did build a flexural testing tower for my biaxial tester using only one of the actuators. And you see, this is a very simple device. I just made a 3D printed block, a rest for the sample. The sample is very small, of course, because it's a real painting. And in this case, we are going to see the results for a mock-up I made for the Nightwatch. So this is the Nightwatch lining canvas, 1975 lining canvas, and this is a 17th century painting lined with the same procedure and materials used for the Nightwatch in 1975. So this is the result of the test, and this is the way the flexural modulus is calculated. You see that the thickness of the sample plays a major role because it's at the third power. So now let's have a look at, because time is running, and let's have a look at the result. So basically, using the actual sample thickness, the mock-up thickness, we have a flexural modulus that is all right. I mean, it's so right because it's not far from the tensile modulus. So, I mean, it's something that you may expect to have. But still, I only found one literature reference in. So I would be very grateful if someone told me that I'm wrong. I couldn't find any basically, because, so let's see, if we only used the equivalent cross-section of the fibers for the two textiles and the additional, and the paint layers on top, we would reduce the thickness from 1.83 to 0.78. And the elastic modulus, the flexural modulus, sorry, would become 20 gigapascal, which is like oak. I mean, it's a bit too much for the paint, for a painting, isn't it? And if we just used the lining canvas fiber section, we would, and the paint layers, just by a slight reduction, we would have 38 gigapascal, which is the expected flexural modulus for fiberglass epoxy composites. So we're completely out of scale. So far, it seems that for the flexural modulus, the most reasonable thing to do is to keep the actual thickness of the material. But this is an open question for me, and for you as well, please. Okay, thank you.
Thank you very much, and of course, questions. We have Cecilia.
Thank you very much for your presentation. Maybe can you go back on your slide where you show the different things? Yes, this one, perfect. Thank you.
Here?
There's a tree of your. I think if I understand correctly, when you make this calculation of your different modulus, you assume this is a continuous material, right? It's like what kind of model do you use when you make this calculation? That is a continuum mechanics, right?
Okay, I'm not sure I heard you, but I'll try to reply. I think I understand. So in this case, we are using it as if it were a continuous material, but it's not, definitely, because it's two canvases with wax resin inside and paint layers on top. So but you know, if you're bending it, and you're bending it from the back, basically you are compressing the lining canvas and you're putting under tension the paint layers. So I mean, it's a complex thing to think about. And so.
Yeah, but what my point is, because you have a complex phenomenon, you are applying maybe a too simple model to calculate your E-flex. Does it make sense to you what I'm saying? Like, I know because in wood science, that's what we do for panel paintings. We consider that the gesso layer, the paint layer, and the wood is attached to each other to calculate E modulus from one layer from a general, like you did. Like we measure one modulus from a general test, and then we calculate theoretically what's happening in individual layers.
Yeah.
But those models, I think they are a bit too simple for your case because your material is not continuous. It's fibers, as you said, it's void samples, and maybe this is, you may need another approach, like with more modeling and so on, to calculate your E modulus for individual materials. That's why it's just a suggestion. It's just I don't know the answer.
Okay, I think I understand your point. This was the very last part of my PhD study, so this is a very raw material I'm presenting here. Yeah. So maybe it was not the best choice to do it, but I really think it's an interesting question, because I only found one thing in literature about the flexural modulus for painting, and it was a very thin canvas painting, which was not only used. I mean, they did not make a 3-point flexural calculation, but they made the heart loop. So so really, I don't really know what's best for this. It's just that in perspective, I know that it's extremely important for digital simulation to have flexural modulus and not only the tensile modulus. And as for the tensile modulus, there is a little bit more thought about, even though I didn't find anything about lined paintings. I think it's an interesting provocation to talk about it here, so that maybe I will learn a bit more about this in time. Yeah, sure.
Can I say something? So we use very similar approach, and recently we published a paper about simulation of the canvas paintings, I think in October. It was released by Heritage Science, and we used the Antonio's approach, very simplified and reduced, and we used just a correction for empty spaces, which Marion Mecklenburg proposed, and we obtained fair agreement with the monitoring of real canvases in real spaces. So I would say it's reduced, but in certain situation can work.
Okay. Thank you.
One more short question.
That's great. Can you hear me?
Yeah.
Okay. It's more of an observation rather than anything else. You're talking about how best to kind of handle the voids. In the textile industry, tenacity is what's used, so the linear density of the fibers. So did you think about, I know you took cross-sectional areas, but rather than calculating the stress from force divided by the area, thinking about the force divided by the linear density of the yarns, because that's how it would be done in the textile industry. And there are issues there, because in the textile industry, you're going to have a more uniform yarn over a longer length and distance. But the tenacity might be one way of approaching some of your calculations, certainly in tension.
Yeah. Okay. I didn't think about tenacity, but I did think about the linear density. But the linear density is extremely difficult to calculate if you have, I mean, I tried, but it's very different to calculate if you have a very, very small sample, because linear density in textile industry normally calculated on spools of 1 kilometer of yarn.
Yeah, a kilometer. Yeah.
So, and also yarns in a naturally aged canvas are contaminated. So you would get sort of a wrongish number.
Yeah, it's a good point. As you say, then they are potentially contaminated. So, but certainly it looked like you had quite a lot of materials. So there might be an extrapolation out, but maybe it doesn't have to be tenacity in its purest sense, but a modified calculation that accounts for a reasonable length of material might be something that you could think about.
Thank you very much for your remark. I would love to discuss it privately, because I'm thrown out.
Time around.
Okay.